So my name is David Ferguson. I'm the co-PI of Northrop Grumman's effort on the QEO program. I'd like to begin by thanking, of course, the organizers of this. I'm a stroller, so hopefully I'll stay locked in here. I'd like to thank the organizers and the staff that makes a conference like this happen. I'd like to thank my Northrop Grumman colleagues, of course. I have a great time working there. I'm learning all the time. The QEO program, and the staff at Lincoln Labs, who we've been working really close with on this program. That's been a great relationship. And of course, IARPA and USC. So I'm going to talk a bit about single qubit effects. We're a starting program, so that will be kind of the major focus of my talk. And you'll hear a lot of the same talks that my friends from Google and D-Wave just went over, so maybe it'll sink in a little bit deeper the second time you hear it. Some new stuff as well. We'll talk a bit about non-stochastic device concepts and implementation. So I wanted to throw this slide up here, and that was put up here last year, but just to kind of talk about the goal of what we're kind of striving for as a community, and that is we want to create computing machines that can solve problems that are application relevant, but by physical methods that are intrinsically quantum. And by that I mean kind of outside of the Church-Turing, extended Church-Turing thesis, which is basically, that any other Turing machine can be efficiently emulated by the next one over. So we want something outside of that, something that's fundamentally different physical mode of operation. So in the context of annealing, of course, there's no kind of, directions of specifically take these 10 steps and you'll get to this promised land, but there's a lot of promising heuristics. So here we go. So here is a more kind of philosophical than mathematically rigorous thought about what is the kind of the possible different types of categories that you can have. So just to kind of give an overall framework, it's one of the earlier talks, so kind of set some philosophy almost of what I want to talk about. So just starting on the left-hand side, just to kind of think of a computing machine and all of the stuff all of the physical processes that are going on inside of it. There's electrons, there's nucleons, but I don't want to think about, quark dynamics. I want to reduce the dynamics down to the part of that dynamics that is intrinsic to the computation. Where is the bit information encoded and what is its fundamental dynamics? And so contained within that, once you have your bits and they're kind of moving around inside of your computing machine, you'd like to find physical processes that are outside of the Church-Turing thesis. So that's kind of where we are focusing for the QEO program. But then I want to put in a subcategory of application-relevant processes. So things that you don't have to care about the intrinsic physics of the device. You're just looking at it for an application. So things that are not. So I'm not talking about supremacy or self-simulation. I want to have a device that can tell you something about another process, not just tell you about itself. So I also want to take a moment to just talk about the difficulties on the theoretical side. And so I kind of have three broad categories here. So you have a computing machine. It's doing application relevant computations. And all the way down at the blue, you have kind of algorithms that are known to give you a speed up. Kind of, for instance, I would put one in there as the fast Fourier transform. Everybody knows how to calculate a Fourier transform by its definition, but there's a separate algorithm. The fast Fourier transform, neglecting logarithmic factor, gives you a linear improvement. So that's a kind of you can prove that that here is an algorithm that gives you a speed up relative to the straightforward approach. And then I want to slightly enlarge that to algorithms that in principle you can, maybe we haven't proven them yet. That's what all our theorist friends are working on, our algorithmic theorists. But it's actually possible to prove a theorem that this algorithm is successfully gives you a calculation that you want. So kind of some goal of some theorists is kind of expand the blue to cover all of the red. but there still yet may be application-relevant computation that's just physically not possible, or very, very difficult to prove that from a theorem point of view that indeed this computing is application relevant. So I want to kind of maintain the possibility that there's this gray area, some things that might fit in there are just various machine learning algorithms and things like this where, you just kind of see that, yes, and it indeed works. But it's kind of a challenge because you'd like to have a solid goal, but unfortunately this field of quantum annealing may not allow, the advantage may be in that gray area. So it's kind of a challenge. So again, just to kind of talk back at the, perhaps is somebody could give me a 5-minute warning? Just raise your hand. Yeah, okay. So just talk real briefly. What is the kind of on that topic of the fundamental bit dynamics? What is the bit dynamics that I want to talk about? Of course, we have our superconducting loops. When it's a very strong superconductivity, you'll have the fluxes quantized, but we just want to have a generalization of the notion of that you can have different windings of your order parameter around a ring that might be interrupted by a Josephson junction. So, but really the thing that we most care about is that vortex state and how those vortices move around. So here's kind of early enough in the conference that we can still talk about it. So you have 2 examples of compound junction SQUIDs, and so how might you change the bit information? You can kind of suppress the effective critical current of those compound junctions, which kind of raises and lowers barriers, and you can tilt and you can kind of slosh the bit from right to left. So that's kind of the essential bit operation. So I just wanted to mention that these CJJ SQUIDs, in addition to the great work that D-Wave's doing, there are classical computing approaches. Here I've talked about adiabatic quantum flux parametron technology. So how does it work? So instead of having just a kind of a global annealing bias where everything happens all at once, here you kind of activate each one of these AQFPs in sequence so that the first one starts, and maybe starts on the right well, and it provides a bias to the next guy. It activates, it kind of goes from single well to double well. It kind of picks up that information from the first one, and that information kind of propagates down the shift register. So I think this is an instructive example when you're thinking about what are the possible things that these type of circuits can do, because it's kind of in the opposite corner from what annealing does. Annealing is massively coupled, and I would say that it's kind of low depth. You're trying to do everything all at once. And this is kind of of course, reverse annealing is a nice generalization, but so this is kind of, very kind of streamlined and very low width, but has longer depth. So this AQFP technologies, so here's a new gate concept that was developed recently, this majority gate, where you take 3 input QFPs, and then it basically goes into an output QFP, and just which way that output one tilts is kind of set by the state of all those 3, just kind of in the majority vote. And you can actually, once you kind of reimagine what a computing architecture might want to be, like they did in this paper, you can start to define primitive circuits like an 8-bit adder. So you can really kind of see you can perhaps visualize the bit information kind of cascading down from the top, going through all of these majority gate things and coming out the bottom there. So what is the kind of classical model that they use to study these circuits? So it's just kind of this double well potential that we saw previously. You have a kinetic energy that comes from your charging energy, and you can formulate it in terms of a Hamiltonian dynamics that we learned in school. And you can of course add in not just the kind of the conservative Hamiltonian dynamics, but you can add in resistive terms, Johnson and Nyquist noise, etc. So there are well-developed. I've learned that there are well-developed these classical simulation tools. One of the ones that's open source is this one called WR Spice. Up in the upper right, there's kind of a screenshot of how do you specify the circuit with a netlist, and you kind of run a command, and you can kind of see qubits, you can see SQUIDs transitioning from right and out. It's a quite nice tool. I encourage people to kind of look at it if you're interested in that kind of stuff. So it's one of the things where, as part of QEO, we'd like to benchmark some of our qubits by doing a correlation analysis where you kind of have quantum models on one side and you have these really nice, well-developed classical models on the other side, and really begin to look at where are the leading order corrections. And one thing that I would like to say is that it's not only important for the quantum dynamics is to understand, when you are achieving some type of dynamics that are fundamentally new, but you can also feed that information back to the engineers that are trying to engineer these circuits on the quantum side, or sorry, on the classical side, where might they be getting excess errors that will prevent their adders from working. So to go to a quantum model, what you do, of course, is you just add hats to all of your operators here. And I've also kind of specified some dimensionless variables. If you go over to the right-hand side, I've emphasized gigahertz and nanoseconds. That's a kind of a key unit as well, as much as theorists don't like to use it. But it really is, I would encourage theorists to really kind of think about what for when you're building a model because there's a lot of fundamental reasons like temperature or control electronics where gigahertz is an important scale. But another one I wanted to mention is the dephasing time and how it's related to the annealing time. That's a kind of also one of these, or the thermalization time. Some of these decoherent rates and how they compare to the annealing time and being in very different regimes. A lot of different implementations of quantum annealing. You can explore very interesting new regimes. So I just wanted to take a moment to talk about different classical models that one can use to model CJJ SQUIDs. One of the ones that has been used previously is the spin vector, where basically you take the classical model, you quantize it, you describe it as a qubit, you get these A and B coefficients, energy coefficients that we all know and love, and then what you can do is you can just kind of take that as an effective magnetic field, but then go back to a classical description of a vector rotating in the external magnetic field. And so, again, so you can take that classical vector and you can kind of look at one of the angles, the angle away from the x-axis as an analog of the phase on your Josephson junction. So one of the things that's interesting is that you get two kind of very different types of dynamics. One, you can see that the oscillations for the SQUID is a bit more narrow, and that has to do with the fundamental impedance of the circuit, as well as it kind of goes through this icing instability, where it kind of has to pick one side or the other as you kind of go through this single well to double well regime. And so whereas the spin vector, its susceptibilities are changing, but it doesn't go through that. So I just wanted to emphasize that as saying that when you are looking for a distinction between your classical and quantum model, you should make sure that you consider all the different types of classical models. So here's some simulations. You've seen these just recently of adiabatic, using the adiabatic basis and these geometric connections that Chris talked about. And so if you go too fast, you can generate coherent transitions between states. That's what the upper left-hand side is showing. So this is a 5 nanosecond anneal, a full quantum simulation. It's showing transitions. But if you slow that anneal down, as you can see in the middle, you basically get this Landau-Zener type suppression. And already by 12 nanoseconds, you're already at around 10 to the minus 3 errors. So you really kind of suppress those transitions relatively quickly. But then, and so in particular, you get this kind of transition width that in theory you should be able to narrow up exponentially fast as a function of an annealing time. And potentially use that transition width as an indication of the quantum behavior. But unfortunately, again, we're kind of in the single qubit regime. Classical noise effects can really kind of blur that transition out. And so it's kind of hard to distinguish when you get a finite transition width. Is that due to quantum effects, or is that just kind of due to classical noise? And so, of course, you have this kind of conundrum of how do you demonstrate that your circuit is intrinsically quantum? So one thing that we kind of looked at, that we've been looking at recently, is the use of an excited state. So excited states, like the first excited state of your qubit, it can be there by unintended thermal processes. You might put a microwave drive on there to create that transition to begin with. So you have there on the left-hand side is the single well regime spectrum. You can kind of see that it's fairly harmonic. And then as you transition over to the right-hand side, you're kind of going into that double well regime. And what I've done is I plotted it for two slightly different values of the Z flux that you're doing this X sweep for, this X anneal for. And basically, you see that some of the states, they shift in their energy relative to the ground state, which means the ground state is in one well, and the other states that are shifting are in the other well, so that when you tilt it, they basically change their energy a bit. And so if you kind of look at that first excited state, so it goes to a state that's in the opposite well. That's why it goes from a solid line to a dotted line, because its energy is shifting relative to the ground state. However, you can imagine kind of bringing that up and further, and eventually it will go back down, and after you anneal it, back into that same lower state that the ground state went into, and it won't. So it won't show if you kind of just say, well, at the end of the anneal, did I get a right hand circulating or left hand circulating? It will go into the same type of readout as the ground state does. So if you look there kind of on the right-hand side, the top graph is a function of Z flux as you go from left to right. So you start with an initial state that has about 20% in the excited state, and you basically see that, oh, no, both of the ground and excited are reading out the same way, and then eventually the excited state is reading out a little bit, is reading out into the opposite well. And then in the middle, they both kind of switch their roles, which wells they're in. And then finally, all the way to the other side, that they're both reading out in the same well. So this kind of characteristic double-step behavior is not something that we were able to generate in any sort of classical simulation. So it's kind of an intrinsic quantumness that kind of, you get these quantized level. So this is an example of an intrinsic quantum effects that kind of let you know that your bits are indeed hopping around your machine in a quantum way. And when you compare that to the experiment, when you have about a 20% excited state probability, you see the same type of steppy behavior that we've seen in the lab. So just to take a slight detour, so one of the important things to think about is, well, what are the right type of application area for this physical system? So one of the things that's challenging is what size of qubits do you want to deal with? Do you want to use qubits that span the entire size of your chip? Do you want to deal with smaller qubits that have strong ferromagnetic coupling? Because once your bit information is kind of spanning larger areas of your chip, it kind of creates opportunities for interactions. But for instance, if you take an approach where you have a large effective qubit made out of smaller component parts, when you look at, how are the effective A and B coefficients of your annealing Hamiltonian derived from the kind of the primitive component part of your qubit? And you can make similar arguments that have made in this field before, that these A and B coefficients, when you're dealing with these encoded qubits, they take on a different time dependence during the anneal. So, and in particular, they can be exponentially suppressed as a function of k, the length of the chain. And so if you have an algorithm that is going to, as you get to larger and larger problem size, the k gets bigger and bigger, this can be a problem for the operation of your machine. It's kind of an important effect that we want to make sure that we are incorporating into the QAO setup. So instead, one of the things that we're thinking about, in part spurred by this work by Alejandro and team, is really kind of trying to find a nice application that embeds locally. So again, one of the ones that is NP-hard is max2sat. But instead of thinking of a general max2sat, really kind of reducing it down to ones that have local connectivity. And instead of trying to say, oh, we need to find the ground state, really trying to just kind of find an approximate solution for max2sat, which is in fact still NP-hard. So here on the right-hand side, I've kind of outlined what are some of the possible things that might happen. One is that maybe what you find is that indeed there are some quantum effects that really allow you to, as this bit information is coherently hopping around your machine, your flux qubits indeed are generating a sampling that solution to 2-sat in a fundamental way that's different from what classical solvers can do, which are there on the right. So here I've kind of said, well, maybe there's one that's made out of AQFP hardware that we talked about earlier. Here's another one that depends on CMOS. And this is an example of you run it for a given amount of time, and you see how well you can find what kind of thing you can find. 5 minutes? Thank you. So I wanted to change that. So here, the only thing that really changed, if you look here, say after time t, after energy E. So you can imagine I have my power plant. I'm going to say I'm going to use, just the energy from this power plant. How well can you sample from this 2-sat problem in a way with your different types of computing architectures? So here, what I've suggested is perhaps that CMOS takes a lot of energy relative to both flux qubits or AQFPs, and so maybe if you're just going to say, well, after an energy cost E, maybe this technology will prove some relative advantage in that context. But unfortunately, the theorists, the quantum Monte Carlo people are very resourceful and tricky. And they may be able to prove that if you have a stochastic Hamiltonian, i.e. one where the ground state can be written down with only real probability amplitudes, maybe it could be that you can always find a classical solver that can do exactly the same as your stochastic qubit. So what might you do to solve that? You might go to a non-stochastic qubit. Okay, so as part of the QEO, we're doing experiments on strong non-stochastic qubits. What do I define as a strong non-stochastic qubit? Strong non-stochastic qubit is a qubit that can have large XX interactions even without any presence of any single qubit fields. So in particular, you could get plus XX without single qubit X or single qubit Z. That's what I mean by strong. And that's really a very tricky thing to engineer. So how might you do that? So you can take a regular SQUID loop, but instead of having one place where the critical current is small enough for that bit information, that vortex to hop over, you basically have 2 places where that bit can kind of hop over. And what you do is you get 2 Hamiltonians, one contributions to your Hamiltonian that comes from that bit information hopping over your left SQUID. And here it is, 0 turns to 1, and it's an X operator. And you can always choose the phase of your basis such that one of those SQUIDs gives you a minus X interaction. However, once you have 2 hopping pathways, what you find is a very generic phenomenon based on the Aronoff-Kasher effect that you get a relative phase between these 2 hopping processes that depends on the offset charge of this island. Okay, and so this is how you can intrinsically add different types of interactions, and in particular, if you force the requirement that the Hamiltonian is 0, because that's what you want to basically get into this strong coupling without any sort of single qubit bias fields, it implies for the scenario that the offset charge that you want to put here is half. And in that region, your Hamiltonian is 0, but you have the ability to couple to both plus and minus X fields as well as to your Z field. So I'll just say quickly that there's a fundamental asymmetry between charge and flux noise. And so when you say, I want my flux qubit to be voltage debiased, a lot of experimentalists will look at you with their eyes like, big and like, why would you ever want to do that? That's what the Transmon did. We got out of that regime. But so I just want to say that there are fundamental challenges here, maybe related to fundamental physics. And in particular, it's basically, as a designer, that's your responsibility to make sure that you have a way to solve that. And I'll just say quickly that there is some, I've recently heard some interesting news coming out of the lab, so the QEO team may have some interesting stuff to share about this in the upcoming future. So here's just a simulation of what this device might do. Again, in this regime, the Hamiltonian, by itself, the single qubit terms are 0. The only thing that is there is these interaction terms, and they can modulate as a function of the annealing protocol. And you can be in a regime where both the X and Z operators are of the same order. So in particular, around, for these parameters, 20, 30 nanoamps. So one of the things that being in the regime of strong interactions gets you relative to single qubits is that it allows you to do physical level encoding. So here's an example of a Bacon-Shor code patch, and here is how both this tunable phase-slip qubit, this non-stochastic qubit, changes as a function of this offset charge. So you get this linear sensitivity to charge noise that's a challenge. But once you go to a Bacon-Shor type of encoding, you see that not only the amplitude, but that it goes from linear sensitivity to quadratic sensitivity. So this is a very interesting regime to be in. You kind of have to take one step back, where you are now sensitive to charge noise, but then the kind of DC charge noise, but you can then kind of engineer back in your insensitivity and retain your non-stochastic behavior. So again, I think that it's a very interesting time where your fundamental bit information is really, of our computing machines, are really entering a fundamentally new type of dynamics, which is quite exciting from a theoretical perspective, and we're making a lot of fun progress in the QEO program.
Any questions for David?
I have a question about the last part. It's so once you engineer this insensitivity, as you say, using Bacon-Shor, don't you have to compromise the control, the precision of the control?
Yeah, there are definitely a lot of compromises. One of the compromises is, for instance, how do you put coupling back in, for instance? So that can be quite challenging, and that's actually one of the things that my colleague and I, Ryan Epstein, have thought about and worked on a bit. But yes, there are, for instance, how do you control it? How do you create couplings? Did I get the point of your question?
Yes.
Yeah. No, there is. You can become insensitive to noise, but then that's just step one. You've got to re-engineer the control. Yep.
I want to ask you a question about the single qubit annealing.
Yeah.
With the excited state, I do not really get why you said that that's truly quantum effect, and what sets the step of that, the height of that step.
Oh, gotcha. So of course, I don't have a theorem to say that I can't get a phenomenon like that with any type of classical model. I can just say that, when we compared our classical models to the quantum model, it wasn't there. And so that was just the quantum simulation that was kind of consistent with the qualitative behavior. So what sets that height is just the relative probability that you're in the excited state. So if you were completely in the excited state, the step would, it would kind of go high and then back all the way low and then back all the way high, for instance. So again, at this stage, we're really trying to say, well, what do we know? How do we know that we're really in this coherent quantum regime? And this is one metric that we were looking at.
All right, let's thank David again.